Alright, let's talk in this video about the number e. There we go. Nice little box for e. So e is the number 2.718281828. I think it's a 4, then a 5. I forget if it's an 8 or a 9. Either way, it goes on. I remember that this sequence repeats, and so it's easy to remember a lot of digits of e, just because like a huge portion of them, in the beginning at least, repeat. But I assure you that those 8s will start showing up later on in longer distances, just because it's basically random how these numbers appear. So e is what we call an irrational number. That means it cannot be represented as a fraction. As you can see here, we write in it what we call decimal expansion because that's kind of one of the few ways that we can write the number. It's also what we'd call transcendental. Is it transcendental? Yeah, I'm gonna guess here. Transcendental means there's no way to calculate it directly. I mean, we can only calculate approximations, basically. It's non-algebraic, which means there's no algebraic way to find it, to get it, I mean. Of course, it's slightly more than that. It means that you can't square root a number. It means you can't square a number to get e. It means you can't do all this stuff. However, as you'll see in the future, or as you might have seen already, you can find it with infinite summations, if you add numbers infinitely, or if you multiply numbers infinitely, which we'll actually talk about today. That way, if you want to know notation for multiplying patterns, it's this little guy. It's a lot like the summation, but it's the capital pi symbol instead of the capital sigma. Whatever, I think that's covered pretty well. So irrational, no fractions. That means you can't write 22/7 is only an approximation of 3.14. It isn't the number though. So yeah, anyway, I think that's pretty covered. Unfortunately, e is what I'd call a very analytical number. That's my name for it. I mean, that's my way to distinguish it from pi. This is very analytical. You kind of have to calculate it. You kind of have to understand the numbers, what you're working with. It's a number, this whole number, that shows up when you're calculating. It doesn't really show up visually. Now, a number that does show up visually is what I'd say pi. Yeah, pi is very visual. It is the ratio of diameters to distance around the circle, or radii to 2 times the distance around the circle. Yeah? Wait, no, half the distance around the circle. Yeah, 3.14 radii go around half a circle, and 3.14 diameters go around a full circle. There you go. So that's how a visual way you can find pi, and honestly, it is basically the circle constant, though we also call it Archimedes constant. Archimedes. I think we've already covered him a good bit. Archimedes constant. So I won't. But what we'll talk about today is what we call Euler's constant. It looks like Euler. And in fact, most people who talk about Euler's formulas who've never heard anyone else talk about them say Euler. That was me once. Not anymore. So Euler's constant. And a constant is just a number that doesn't change. Basically, we have the gravitational constant. That is a really small number. It's like something times 10 to the negative 11. That means you're dividing by 11 times. So it's a pretty tiny number. But it doesn't really change. And so does Euler's constant not really change. Stays constant. So Euler's constant, though, is one of the finest. I also like thinking of it as the natural number. You'll find that it is a very natural number that comes up with numbers in general. As numbers go, this number is actually very natural despite how it looks, it being endless and so forth. So, why don't we jump into it history-wise first? So this guy named Bernoulli, I forgot if it was Johann or Jacob Bernoulli, but needless to say, it was a Bernoulli. The Bernoulli family, I talk about them all the time because they've discovered a ton of things from mid-1600s to mid-1700s. This whole family of people with the last name Bernoulli who discovered things about fluid dynamics, who discovered things about differential equations, who discovered other calculus concepts, who discovered probability concepts. Bernoullis were crazy men. I'm sure there's women in there, but none famous, I don't think. It's the times. So that was 1650s, whatever. In about 1700, I think it was maybe 1712, maybe it was before 1700, though. I believe it was Johann Bernoulli, I'm guessing here a little bit. But it was one of the Bernoullis, and they discovered this 2.71828 whatever number. And let's just talk about how he discovered it. So what did Bernoulli do? So usually, math comes after a change, after a system is created. I mean, in history, it does. The reason Greeks even started was because during Babylonian times, we invented stuff like the bank, and we started selling plots of land. So we'd have to measure area and stuff for that. And I think we'd even sell volumes of liquids and stuff like that. And so there was definitely incentive to understand why and how we're doing these calculations. Because I believe we kind of just came up with this idea for area on the fly. It just kind of worked out, giving us good numbers. But that's not how you really do math. I mean, math is basically answering the question, why are we doing it this way? And so, over time, something changes in a system, and mathematicians investigate it, try out different systems, etc. And, I mean, sometimes it's useful, sometimes it's a total joke. Not joke, but something fun to do, which I think is the majority of math, but I don't mind at all. It's a lot of fun. But, needless to say, what happened during the 1600s was a rise in probability because in the 1500s, we had a lot of basically bar games, a lot of like early bar games where you roll dice and predict what the values will be and stuff like that. Lots of those games sprouted up questions like, how should we divide the money we put down if you have to stop a game early? That's the question that started probability in the 1600s. But what continued in the 1700s, after probability was started, we actually created jobs like I believe like health insurance. We basically put a price on how much someone would cost when they're dead, and so you need probabilities for that. And with the rise in insurance, I'm pretty sure we also had a rise in banks loaning money. And when a bank loans money, they offer this thing called interest. It's an increasing amount of money based on the time. It's basically the amount of money you earn for storing or lending your money to a certain place. And it's dependent on time. Interest is a way to talk about money where the time actually matters. I mean, $50 back in the day might be worth $100 today. That might be inflation or something like that. Or, I mean, that would be inflation in that case. But the reality is, the value doesn't necessarily change. The number changes on it, but the value of the currency is still currency, whereas interest does depend on time. All I'm saying is that time matters with interest. I'll just put T. T dependent. How is it dependent on time? I think you should know this pretty well. Let's set up a system just to get some practice with using it. Then we'll actually investigate it the way Bernoulli did. And then I think I'll push another video where we'll actually where we'll investigate E. Like, why is it called Euler's constant, not Bernoulli's constant? It has to do with Euler's discoveries about this number E. But either way, let's get into this. So let's say you have 5% interest annually. Is it two N's? I think it's two N's. Maybe it's two L's too. Yeah, if it's wrong, whatever. So 5% annually. That means every year, every annual, basically, we add 5% of our initial value of last year's value to itself. Yeah, let's just see this in action. So let's say we put $20 down into this bank that offers 5% interest. Put $20 in. So that'd mean after 1 year, you take 5% of $20. Let's write it this way: 5% times $20. Then you add it to that $20. It wouldn't make sense to take 5% of $20 and just give them that. That'd be taking 95% of their money away, which would be bad. It would also not make sense if you subtracted it, because that would be leaving them with 95%. When you store money in a bank, you're getting money because you're storing it there. And so that's basically the idea here. So you should be gaining money. That's your initial. That is what you're adding to it. This is also what we call principal, because this is the initial. Let's create a little timeline. Let's go up to 3. Initial year, first year, second year, 3 years. Alright, so $20 after no years passed is $20. After 1 year, 5% of 20, what is that? 5% is 5 out of 100%. Cent means 100. So you can rewrite that actually. 5 divided by 5 is 1. But if I divide this by 5, I have to divide this by 5, which I chose 5 because it goes perfectly and becomes perfectly 20. So 5/100ths, or 5% of 20, is same as 1/20th of 20, which is easy, 1. And so knowing that means after 1 year, we gained a whole $1. Yay. We got a whole $1 for leaving in for a year. That's not very good, but whatever. We're going to stick with his bank. It could be worse. It could be less than 5%. So now we do this again. We take this whole value, multiply by 5%, 0.05, then add it to itself, which is $20 plus 20 times 0.05. So what you'll find is every time you do this, you do the same sequence. You multiply by 0.05 and then add it to the value inside the parentheses, basically. But this gets big and messy fast, and that's why I haven't written anything on that side of the plus sign, because I know it would be horrible to write out. But there's actually a pattern here for each time it's being added. In fact, this is called an exponential growth. Even though exponential is just multiplying, this is actually just multiplying. We just have to write it differently. So let's write it in notation. So we have our principal, P, and we have a rate, which is our percentage. So P, and we add our percentage of P, our rate times P. So that'd be 5% times P. And we add them together. That is the first sequence. The second sequence is rate times P plus RP plus our P plus RP, because that's what's in parentheses. That's our initial that year. Our current, basically. And so we multiply it by that rate, 5% of that whole value, and then add it to itself. It wouldn't make sense to keep taking 5% of this value, because that's not what you have in the bank anymore. Yet you've technically invested more money in the bank, and so you earn more for it. But it still doesn't grow that fast. They give you small percentages, even smaller than 5% often, because they don't want to just give away a ton of money to you just because you're using the bank. Because they have a lot of people using their bank. Either way. So this is the pattern, and it gets messier. So that's a way you could write out a scenario after 2 years, and initial year is P. But there's actually a pattern here. This is where factoring becomes genius. This is P times 1 and P times R. So you can write it as P times 1 and p times r. Alright. Alright. That's dumb. Alright, so we have p times 1 plus r. P and p times 1 plus r. If you look at this, rewriting as that, you have p times 1 plus r times another r plus a p times 1 plus r. Guess what? There's a p times 1 plus r in both of these. This is p times 1 plus r times r. So we can write it as p times 1 plus r times r. And this is p times 1 plus r times 1. If you look, there's r plus 1 multiplied twice, so that's the same thing as p times 1 plus r squared. And check it out, you can see this pattern happening. It is exponential because by the third time, guess what? You can just guess the pattern here. It's p times 1 plus our rate. That's an r. It looks like an n or some other alien writing. 3 times, you multiply 3 times. By the third year, you multiply 3 times. You just multiply. That's easy as that. So this system is a lot more sensible, multiplying by 1 plus r. In fact, this is 1 plus r to the 0 power because anything to the 0 power is 1, and so it technically doesn't show up, even though it is there is technically a 1 there. So this math works out. So we can be confident our equation here is p times 1 plus r to the t. That's how many years have passed. And that is our amount. AT. Cool. Page 2. Now let's do a little more. Now that we have interest covered, and the way we'd write this equation, sorry I never wrote it, is 20 times 1 plus 0.05, because that's 5%. So we get 1.05 to the t power. Now the reason that adding one business works is because the way I think about it is you have 100% plus your added percentage. Then you take that 100% plus your added percentage. Then you take this 100% plus the added percentage. And it keeps getting bigger and bigger exponentially. So after 1 year you can check 20 times 1.05 is definitely going 20 times 1.05 is definitely going to be 21, like we said here, just doing it the other way, the long way. Now this calculation, which is less pretty, but you can write it simply, 1.05 multiplied twice. So you can write times 1.05, or you could just square it if your calculator does that business. So now we get 22.05. If you look, this change is getting bigger. This change is 1. This change is $1.05. So it definitely is getting bigger. Then 21.05 to the third power. So after 3 years, we gain $3.15. So 23.15. Cool. Now, of course, you have to round because you can't give them fractions of cents. In a bank, I believe, they store fractions of cents. But in your hand, you're not going to have a fraction of a cent. All right, so that's the business of what's going on. You just multiply by that 1 plus that percentage. It's confusing to write this way because it hides the fact that you're actually adding it on each time. All right, now let's go Bernoulli style. By the way, this sheet, just to let you know, is just an ink sheet, so you don't bleed through to the next page. Looks like I do bleed a little bit, but whatever. You make sacrifices. Alright, so let's go to what Bernoulli did. He asked the question, when we had, let's say this scenario, what happens if I did this over smaller amounts of times? Instead of doing 5% annually, why don't I do 2.5% semi-annually, so twice a year? Because if I do 2.5 twice, I get 5. Turns out you get a slightly different result. In fact, a slightly higher result. But let's look at this. So we have p times 1 plus our rate to the t power. All right. That is how you calculate your amount at that time. Alright, P, and this is this function notation, amount at that time. This is multiplication, principal times that. So what he said is, I want to investigate what happens when a principal is 1. It's a very simple choice because then the principal basically disappears from math. What happens when our percent increase is 100%? That is also very natural because if you know 100% is also 1. Now you might think, yeah, let's plug in 1 for r, but it's not that simple. It is plug in 1 for r, but then you divide it by how many times you want to multiply it. Also, he also contemplated this over a 1-year period. Because if you make t1, it also disappears. So by plugging 1 into all this business, you get 1 plus 1. But that's not the true story because you want to multiply it that many times in a year and then divide it that many times that you multiply it. It's kind of like that, what I said out loud. 5% in 1 year is going to be similar to 2.5% in twice a year, because both of these multiply to the same value. Basically, that's the logic here. This is how many times you multiply it, this number, and this number is what you're cutting it into. Except for rather than cutting up 5%, we're cutting up 100%. So this formula is what you want to know. 1 plus a fraction of 100% multiplied x amount of times. So let's just contemplate what happens in 1 year if you do it twice a year, if you calculate this twice a year. Now it should be noted, just really fast, what we're trying to do is create a natural number, natural growth. Because this isn't natural growth, this comes from a banking scenario. Animals don't really do banking. I mean, that feels like a silly thing to point out, but it's true. They don't have these computers, they don't have these calculations they can do on the fly. They grow naturally. So we want some way to quantify natural growth. And the way things grow naturally isn't you wait a year and then, whoa, all of a sudden it grows to that size. And then wait another year and then it doubles again. No, you don't do that. That's not how things grow. Things grow maybe this at this instant, maybe this at this instant, maybe this at this instant, maybe wait a month. Hey, it's a slightly bit bigger. Yeah. Maybe wait another month. Oh, it's slightly bit bigger. But it's constant. There's constant growth. And so that's what we want to quantify. How can we get constant growth over 1 year with this formula? So we're using a banking formula and making it as natural as possible by cutting it up into more and more pieces. That's the idea here. So let's actually do it in practice. If we did it in 1 year, you get $2 at the end. If you did it twice a year, you'd want to do it in segments of 50%. So you put in 1, 50% of 1 is 0.5, so you add it to it. 1.5, 50% of that is 0.75. So then you get 2.25 when you add it. So this is our final value. It is getting bigger just by doing it twice a year. This years on this axis, this is your amount at that time. Now if we do it 4 times, let's just skip to the end. So you take 1, I want to make sure you can see that. 1, you multiply it. So 1.25, that's what that is saying. So that's is it 3 months? Yep. 3 times 4 is 12. 12 months in a year. And you multiply it 4 times. Check that out. We get even more money. So let's just create a table here. X and 1 plus 1 over x to the x power. So at 1, when x is equal to 1, you get 2 after 1 year. After 1 year, for splitting up into 2 times a year, 50% each, you get 2.25. You get about 2.44 if you do it 4 times a year, also every 3 months. Let's do it every day, all right? So that's 1, split 100 among 365 days, we're assuming a normal year. And then you multiply it 365 times, because that's how many times you're calculating it. And so we get this number 2.71. That number sounds familiar, but whatever. I'll just write it down. Now let's do one more. We can do one better. In fact, you can gain a maximum of 1 cent more to get 2.72. Just to demonstrate, let's do every hour. So that's 365 divided by another. So there's 24 hours in a day. And then that's taking it to the 365 times 24. We divided twice here, we multiplied twice here. And here we go. 2.7181 and whatever, but you can round it up to 2.72. So that's 365 24 hours. So that means we're calculating this every hour. So if we did it constant, what would we get? 1 plus 1 divided by, let's just type in the big number. So that's 1, 2, 3, 1, 2, 3, 1, 2, 3. That's like a billion, maybe? I don't know, I'm not going to count. 1, 1, 2, 3, 1, 2, 3, 1, 2, 3. I might have not typed that in wrong. Just, if I get it wrong, I'll find out. Oh good, I typed it in perfectly. And let's compare to the number e. They're like identical. Okay, minus the last few, but that's just because we haven't taken it to infinity, like I suggested, splitting it up infinitely. But you don't have to, because we have enough numbers to calculate with. So we can now have a constantly growing thing, a thing that grows at every single instant here, and we know it grows at a rate of e in a year, if it was constant. But recognize that's 100% growth. Just because it's natural doesn't mean it's the growth we want. But it's actually pretty easy to have e to the growth you want. That's 100% growth. Know what 50% growth is? 0.5t. So that means you're doing it in half the amount of time you would in this case. This is 50% growth. You can know that if you know derivatives already, because if you take the derivative of this, you get 0.5 e to the 0.5t. This is 100% of itself, so when you take the derivative, you get that. 100% growth, this would give you 0.5 e to the 0.5t. Either way, all I'm getting at here is that it even checks out with calculus, that you get 50% growth in that case. And if you want 150% growth for your thing growing, you just multiply 1.5t. So now we can write the master formula, but it should be noted that Bernoulli discovered this number. He didn't really take it to this next level that we're about to really fast. And then I'll continue in the next video. So we get this new equation. E to the rate that it grows times time. This is kind of a different, this is the rate that I'm talking about, but recognize it's continuous. That's why this number isn't 2, because 2 works. It just skips amount of time. Because you start out with 1, you get 2 at the next value, then you get 4. But that's skipping this time to double. Skipping this time to double, which is not natural. You want to grow over time. Grow off of yourself at every moment. So it's e to the rt, but remember, we just multiply by our principal. This is your master formula for growth. In fact, I'll put it growth at time. This is the percentage that it grows each time, and this is your principal, your initial value. Ta-da! We're done. Try it for yourself. See if all my methods work out, and if I didn't cheat the calculator, or if I did. Thanks for watching.